Now we're going to look at the application of Gauss's law to allow us to calculate electric field values. So the easiest way to show this is by an example, and we're starting out with the solid spherical conductor. So if we are given a charge distribution to consider, where we want to calculate the electric field around this charge distribution, and we are not told what the charge distribution is in terms of the sign, assume it is positive. So this black ball that we're looking at here, this cross-section, we're assuming is a solid metal ball plus charge uniformly distributed on the surface. It is uniformly distributed on the surface because of the rules of electrostatics. If we were to charge this ball, let's assume these are conventional charge carriers for the moment, so the positives we're going to allow to move just for this discussion. Conventional charge, if we put all those positive charges on there, they would repel each other till they could repel no more. They would push to the surface. They couldn't push left to right in terms of moving along the surface anymore. Everything is electrostatics, uniformly distributed on the surface. And as it says here, we know that the electric field equals 0 inside of all conductors. So this is a little bit of a trivial example. That's why when I have here, which you definitely need to get into your notes, you must show all the numbered steps. I'm going to show you those numbered steps in the Roman numeral 2, or the second part of our calculation, where we're looking at the electric field from little r equals capital R out to infinity. Right now, we know that the electric field from 0 to capital R is 0 inside of the conductor. When we use Gauss's law, always, whether it's this trivial case where everything kind of drops out, or whether it is a more complicated case, what we are going to do is always start with Gauss's law. So flux equals integral E dot n hat dA equals Q enclosed on epsilon naught. So use both equal signs, all three terms, when starting your calculations using Gauss's law. Here we can see that we very quickly lose everything because Q enclosed is 0. So our Gaussian surface, which we put inside, so you will always put your Gaussian surface anywhere in between your limits. So in this case, my limits were 0 to capital R. That's important. Your Gaussian surface goes anywhere in between. It will go symmetrically into the problem, and you let it sit there. There's no Q enclosed. That goes to 0. So the only way that this integral can be 0 is if the electric field itself is 0. So we can use Gauss's law to get the result that we know is true. E must be 0. And when we're going to make our graph, we know that the electric field is 0 from little r equals 0 out to capital R. Now, the more interesting and the more important one for you to understand from this page of notes is our next example, the Roman numeral 2 region, where instead of going from 0 to capital R, we're going to go from capital R to infinity. So let's take a look at that solution. All right, so here, now I'm showing the numbered steps, so please number them. They don't have to be in this order. Certainly, but you need to show all of these steps to get full credit for a quiz or test question using Gauss's law as a means to calculate the electric field. Well, the first thing you want to do is to write down Gauss's law. So the integral E dot n hat dA equals Q enclosed over epsilon naught. All right, so just write down Gauss's law. Go to our region of interest. So we're now not going from 0 to R. We are going from R to infinity. And that is where your Gaussian surface goes. Anywhere in between capital R and infinity. So as long as you draw it in, you show it to the grader, it's drawn in symmetrically within the problem that you're solving, you're in business. So Gaussian surface shown, Gauss's law equation shown, perfect. The next thing you want to do is to put in the n hat vector and the e vector to show the cosine value. So it'll either be cosine of 0 or cosine of 180. In this case, we have the electric field due to a spherical geometry, which mirrors the point particle. So for all spherical geometry charge distributions, the electric field will be KQ on little r squared r hat, so that's why the electric field vector goes up. The n hat vector by convention points outward from closed surfaces, so that's where we get our cosine of 0. So show the n hat vector, show the e vector, show that you get the cosine of either 0 or 180. Now, the next thing you want to ask yourself is Q enclosed. What is my Q enclosed? And if your answer is that your Q enclosed is every bit of it, so everything in the problem, in this case, all of it, then you just replace Q enclosed, as it shows here, with capital Q. Now, the symmetry that we insisted be there because we put our Gaussian surface symmetrically, right, about our charge distribution, is important because it will always allow us to take E out of the integral. So E will always come out of the integral, and we want to make sure that we know the grader knows our justification for doing that is that it is constant on the surface by symmetry. Please do not leave this rationale out. Constant by symmetry, E comes out. Now, the integral, the dA in Gauss's law, will always be the Gaussian surface, not the charge distribution itself. So it's not the area based on the charge distribution. It is the area based on our Gaussian surface. Mathematically, integral of dA equals A, so we have our EA, capital Q over epsilon naught. You can see our math works out very nicely. The A goes with the Gaussian surface, so that's why it's a little r squared here. E equals then 1 on 4 pi epsilon naught, capital Q on little r squared, where r goes from capital R to infinity, and voila, we have our graph. So these are the steps that you want to follow for all the Gauss's law application proofs, derivations to show the electric field outside of these charge distributions. As it says here, make sure you label all your graphs. The graph itself would have to be shown. If we can label a max value, we definitely do, so we should just add here that the max value will be when little r equals capital R. So if we were given numbers, we could have an actual electric field max value to look at. And that is it. So this is the basic procedure that we're going to follow. We're going to use it for many different charge distributions and geometries. We're going to talk more about that on our coming pages of notes. But these are the basic formula, the basic structure, the basic mathematical method that we're going to use to calculate these electric field values. So please, as always, ask questions if you have them.